Hi, calculus students. Today we are going to talk about section 3.4. So please make sure you have your notes, something to write with. You'll want a calculator also. All right, so let's get started. It worked. I didn't have to do it 3 times and pause my recording. Okay, so we're going to talk about inverses of functions and relations today. So you might remember some of this from last year. So here's a summary of some of the things from last year that might be familiar to you. So first, inverse relations are inverses if and only if one relation contains the point AB whenever the other contains the point BA. So basically inverses are where the X and Y coordinates are interchanged. Inverse notation, so if our original function is f of x, the notation we use for the other is f with a -1 as a power of x, read as f inverse of x. Okay, we saw that notation back in chapter 2 when we talked about matrices. What inverses look like geometrically is they are reflections of each other over the line y equals x. Right, to algebraically determine inverses, we're going to interchange the x and the y. We're going to solve for y. And then to prove that two functions are inverses, we're going to show that f of g of x and g of f of x are equal to each other. All right, so example 1 asks us to graph the function and its inverse. So we know for f of x equals x squared, that's one of our parent functions, and we know what that looks like. If it helps to make a quick table, then make a quick table. You don't have to. This is one where you should know what the parent function looks like without a table, really. But let's get a graph of that. This is my original function. So the idea with inverses is that the inverse is where we interchange the x and the y coordinates of the original function. So if this is my f of x right here, then to get f inverse of x, so I'm going to use that -1 as a power, so f inverse of x, and this is just asking for the graph. All I have to do is interchange each of these x and y values. So here I would have 4, -2, 1, -1, 0, 0, 1, 1, 4, 2. And I would plot those points. So this is going to be my inverse. So I'm going to plot those points. Oops, 1, 2, 3, 4, and then -2, and then 1, -1, 0, 0, 1, 1, and then 4, 2. So here is the graph of my inverse. Oops, right there. Okay, so you see that idea that they are reflections of each other over the line y equals x. Okay, now another thing that we're going to be talking about here is whether or not the inverse of something is a function. So whether or not the inverse of what you started with is itself a function. So my initial equation that I was given, that is a function, right? It passes a vertical line test for every x value. There's exactly one y value matched with it. How about now for my function? Is my function an inverse? Would it pass a vertical line test? In my table for each x value, is it paired with exactly one unique y value? And I can see here and here, it's not. Or here and here, right? For these x values, there are 2 different y values. So my inverse is not a function. Okay, so we're going to talk a little bit more about that in a second. We have a whole rule about it. And then let's also, while we're at this, talk about how we could find the inverse for this using this idea of interchanging the x's and the y's and solving for y. So remember, f of x I can think of as y equals x squared. So if I interchange the x and the y and solve for y, so I take the square root of both sides, I would have y equals, and don't forget when you take the square root of both sides when you're solving, it's plus or minus the square root of x. So we could write f inverse of x equals the positive or negative square root of x. Okay. It's important to have the positive or negative because if you didn't, then you would be saying like just that top half there is your inverse, but that really wouldn't be the inverse. That would only be reflecting like this little section here, not the whole thing. That's why you need the plus or minus. And you only include that if you're taking even roots of things. So if this was a cube root, you wouldn't be including the plus or minus there. Okay, so we're just talking about inverses and how we can tell whether or not an inverse is going to be a function. And so here is another example of a parabola. We had just talked about that parabola, how its inverse was not a function. Because when you turn it, it makes it so it wouldn't pass a vertical line test. So if I want to be able to tell if the inverse of something is a function, what I can do is instead of applying the vertical line test after I've actually graphed the inverse, what I can do is I can look at the original function and apply a horizontal line test. So if every horizontal line intersects the graph of the relationship in at most one point, then the inverse is a function. So you see here in this parabola how a horizontal line could hit in 2 points. That means this inverse is not a function. Whereas with this cubic, it would only hit 1, so the inverse is a function. Okay, so let's look at example 2. It says consider f of x equals x squared minus 4 is the inverse of function. Explain, and then find the inverse, and then graph. So first of all, we know that's a parabola. So we should be able to answer part A without graphing it. Graphing it doesn't hurt anything, but we should be able to answer it based on knowing our parent functions. We know this is a parabola. We know it's shifted down 4. Would that pass a horizontal line test? No. So the inverse of f of x is not a function because f of x fails the horizontal line test. I'm just going to write HLT. It's important here that we're really specific about what we're referring to when we talk about the horizontal line test. Because if I say the inverse of f of x is not a function because it fails the horizontal line test, the it is referring to the inverse. And if you're looking at an inverse and trying to tell whether or not it's a function, you wouldn't use the horizontal line test, you would use the vertical line test. Okay, so the horizontal line test is only used when you're looking at or referring to the original function. So I'm going to write here, I don't want to see you using that pronoun it unless you're being very, very careful about it. Okay, now the other way you could explain this, it would be perfectly fine to say the inverse is not a function because it, here it's okay because my it is referring to the inverse, and I'm going to say it doesn't pass the vertical line test. Now that's okay because my it is referring to the inverse and the vertical line test. That's okay. If you're trying to use the HLT, the horizontal line test, you shouldn't be using that word it. All right, so then finding the inverse. So try this on your own. We're going to use that same idea of switching the x and the y and then solving for y. So I would add 4 and take the square root of both sides. So y equals positive or negative square root of x plus 4. And then I could write that using the inverse notation. Really, it doesn't matter the order you do any of these 3 parts. You could do them, doesn't matter the order. All right, and then to graph each of them. So to graph each of them, you could use the parent function, and then I know that it is moving down 4, and then I could reflect it over the line y equals x. Sometimes with a flipping over the y equals x can get a little bit tricky just to look at. So I'm just going to do a quick table. So negative, and usually it'd be negative 2, negative 2, 4, right? But now I'm going down 4, so it's 0. And then this would be negative 3, this would be 0, negative 4, this would be 1, negative 3, this would be negative 2, 0. Right. For my inverse, remember, all I have to do to get my inverse is interchange my x and my y. So I'm going to take all of these points and I'm just going to flip them around. So I find that for graphing the inverse, I could do it off the equation, totally could do it off the equation if I have the equation. If you don't have the equation, then it's helpful to just look at your table. Oops, this is wrong. And then just so you know, not every function can have an algebraic inverse. So here I could solve this for y easily. But what if it was an absolute value? Like if you had something like y equals the absolute value of x, and I said, find the inverse, the directions actually would not ask you to find an equation for the inverse because it's not possible. Because if you go like this and say, okay, solve for y, we don't have an operation defined to be the inverse of the absolute value. There would be no way to find it. Now, if I asked you to graph it, that you could do, right? I could make a table for this and I could interchange my x and my y and I could plot the points, but I couldn't actually find the equation. I think that comes up in the homework, which is why I'm mentioning it. Okay, so here is my initial function, right? My parabola that got shifted down 4. And now I can plot this, or I could say, whoa, this is a square root graph that's been shifted to the left 4. So I could just go 1, 2, 3, 4, here, here, and I could plot, and then, oh, I've got to flip it, and then I could go like this, and I could get my inverse that way. I could just use the equation. Or, like I said, you can also use your table. So do what works for you. But you see what I mean, where like if you just try to flip it over the line y equals x, it sort of gets a little tricky, just everything gets muddled because they end up overlapping. But you can kind of see there's that line where they reflect over each other. All right, so go ahead and read example 3 and think about how you might start that one. So fixed costs for manufacturing a particular stereo system are $96,000 and the variable costs are $80 per unit. Write an equation, I should say write an equation that expresses the total cost. C of x is a function of x given that x units are manufactured. Okay, so the cost, right, the cost equals, I know my fixed costs are $96,000 plus $80 per unit. So 80 times the number of units. So now it says determine the inverse process and the equation for the inverse process and describe the real world situation it models. Okay, I'm not going to switch my x and my y, but what I'm going to do is I'm going to solve for the other variable, right? That's kind of what you're doing anyway when you find inverses. So I would subtract the 96,000 and divide, by the 80. So x equals the cost minus 96,000 divided by 80. Okay, so it's the number of units that can be made for a specific cost. So for a given cost. So part C says, okay, determine the number of units that can be made for $144,000. That's my C of x, right? So x is 144,000 minus 96,000 all over 80. Okay, so put that in your calculator and figure it out. 600 units. All right, so the last thing that we need to talk about that was on our initial list of fun facts about inverses, what is the fact that to prove that inverses are functions, you want to show that f of g of x is equal to g of f of x and that they both equal x. Okay, before we get into that, so I'm going to, first I'll write that up here. You have to show that f of g of x equals g of f of x and that they both equal x. All right, so why does that even work? So let's say I had some variable, some value. Let's say x equals, I don't know, 7. And I did something to 7. So I started with 7 and I performed an operation on 7. So let's say I added 2 and I got 9, right? Now, if I were to do the inverse of adding 2 to the 9, so if I started with a 9 and I did the inverse of adding 2, which is subtracting 2, what do I end up with? 7, which is what I started with. So that whole idea of f of g of x and g of f of x, that they both have to equal x. So if I start with a number, I perform an operation on it, and then I do the inverse of the operation to that answer, right? That's the composition thing. I should end up with what I started with. Now I have to show that works in both directions. So if I started with a 7 and then I subtracted 2 and got 5, and then I took my answer and applied the inverse operation, which is to add 2, I also get 7. So that is what this up here is implying that you need to do. So you need to show that if you take something and you do the operation and apply the inverse operation to it, that they're inverses of each other. So here you're given 2 functions. right? It says determine whether they're inverses of each other. Now the homework and the tests and stuff will often ask you to verify that they're inverses, implying that it always works, sort of like when we did the trig proofs, right? You were verifying those identities. So you're not going to have any that don't work. If they don't end up giving you X, then something went wrong algebraically. Okay, so first I'm going to figure out what f of g of x is, and then I'm going to figure out what g of f of x is. So you do have to do it in both directions. On the test also, it will say use composition of functions to verify that they're inverses. So what you cannot do is you can't take this, go through, find the inverse and say, oh, it equals this. And then take this and find the inverse and say, oh, it equals that. Okay, the directions on the test will say use composition of functions. So make sure that you are using composition of functions. Okay, so f of g of x. That means I'm going to take, so I'm going to take my g of x, which is this, and in my rule f of x, I'm going to substitute that in place of the x. So I'm going to have 3 times in place of this x. I'm going to put that whole thing. Okay, so I rewrote this, but in place of this x, I put that whole thing. Okay, so it's still got the squared and all that. So the idea is when I work it all out, I should end up with x. So when I square a square root, they undo each other. So you might be looking at this saying, wow, that looks really complicated, but it should all work out nicely. Those cancel because they're inverses. These cancel because they're inverses, and we get x. Yay, that's what we wanted. Okay, now we have to do it the same idea, but going the other way. So this is g of f of x. So this whole expression for f of x now needs to go into my g rule in place of the x. So now I'm going to have a big square root. In place of this x, I'm going to have 3x squared plus 7, and then minus 7 over 3. And again, when I work that all out, it should just be x. So here these go. Now you do have to show your work. I mean, you know it's supposed to be x, but you can't just say, oh, yep, I did it all in my head, it's x. You need to show your steps, please. Okay, so I get x. Last thing, because like I said, you're going to be asked to verify things, is you need a conclusion. And the conclusion is really always going to be the same. You're going to say something like, since f of g of x is equal to g of f of x, and they both equal x, f and g are inverses. Okay, really same line every time. What could change is maybe I give you functions that are f and h or g and q or whatever. Okay, so, but you really want to make sure you include the conclusion. Okay, otherwise I have to take points off. That stinks. Okay, all right, so that takes care of our summary of inverses. Take care, everybody.